Okay, hello everybody. Welcome back to Comp 3430 Operating Systems. I hope that you have all had a good weekend. I hope that you are staying warm today. I hope that I did not destroy your weekend this weekend. I really hope that I didn't destroy your weekend. When I was coming into work today, I took this picture from the parking lot. The sundogs were spectacular today. They looked amazing. And it's kind of this reminder for me that even when it is feeling like ultra cold on a morning like this, I don't know, there's really cool stuff that's happening because it's super, super cold like this. And yeah, I thought that they were spectacular. And related to sundogs, I did go to see the Dogman movie this weekend and highly recommend it. And I'm only if you've read the Dogman comics. I don't think that you'll appreciate it very much if you haven't. But yeah, I thought it was hilarious. And my mother-in-law was with us when we went to see this movie, and she couldn't stop talking about how she thought that I thought the movie was funnier than my kids thought it was. So yeah, take that for what it's worth. Let's talk about operating systems. So by the end of today's lecture, what I want you to be able to do is, I want you to be able to write some code where processes communicate through message passing, specifically through the use of this thing called a signal. We're going to write some code that will get our processes to be able to effectively stop and listen for an event happening. This is our signal structure. I want you to be able to describe approximately how the operating system supports and implements shared memory, pipes, FIFOs, but signals. Today, I want us to focus on signals. The main thing that I'm going to be talking about with this is kind of a hand-wavy, this is what the OS is doing approach. We could look at what the OS is actually doing. We can spend some time taking a look through the Linux kernel source code to see how it's implementing this signal structure. And while I believe that's a valuable lesson to follow through with, it's getting to be like stepping through some hairy-looking C code, and I don't really want to spend a lot of time doing that, so we're not going to. But we're just going to like do some hand-wavy stuff about the overall structure of what our OS is doing in terms of supporting the implementation of these signals. The other thing that I want us to begin to do is compare and contrast the shared memory and message passing programming models and their relationship as seen through the lens of synchronization. There's a lot there. There's a lot to unpack. The main keyword that I want to point out here, honestly, right now, is that word synchronization. We've seen this now once in the context of two processes that are related from this parent-child relationship, synchronizing themselves. My parent process can block until the child process has exited. And what that means is that I can guarantee the order of events happening here. Certain statements that are happening in my parent process will not execute until my child has exited. And I can make guarantees about the order of execution here. We're going to continue with this in terms of signals today. So we'll think about some uses of what signals can do for us in terms of synchronization. And then when we're looking at threads, we'll think about this idea of shared memory. Yeah.
You said to remind me to try the redirecting the input and output to the same file when we're doing put char and get char and stuff.
Redirecting input and output to the same file. I actually don't remember the context of that. I'm really sorry. What were we doing there?
So like we were working with put char and get char, or like printing in like standard input and output and redirecting those to the same file so that if we have something in that file, we're reading that in and then printing out to the same file.
Okay. Oh gosh, what lecture was that even in?
I think last Monday.
I mean, it's the basic I/O program that we were using for this, right? So there's get char here, and then there's put char. So I'm going to, actually, I'll just do it this way. I'm going to say basic I/O readme.md to readme.md. So this is taking standard input and replacing it with readme.md, and it's taking standard output and replacing it with readme.md. This is going to be shell dependent, I think, and I think what's actually going to happen, this is my prediction. I'm going to let you make a prediction of your own. My prediction here is actually readme.md is just going to get replaced with nothing first. Then getchar will get blocked because there's nothing in readme.md, and we'll just be stuck here. That's my guess. That is my guess. That's my prediction. Take 2 seconds and think of a prediction. All right. Well, actually, that does make sense. So there was nothing in README, and then we did that print statement, and it got put out to standard output, and then there was something suddenly to read in it. I guess that makes sense. Yeah, okay. I forgot all about that, so thank you for reminding me to do that. I don't know if that explains anything to anybody, but I'm glad we did that. Yeah. Okay. So we're going to revisit this idea of synchronization repeatedly now. We're going to be thinking about it in terms of the way that signals can help us with this. We're going to be thinking about it in terms of the way that pipes can help us with this. And then later, we're going to be looking at this from the perspective of using threads. And the structure that we're going to be using with threads to implement this is something called a lock. We don't really have locks in multi-process stuff, but we are going to see locks in multi-threaded stuff. But they're ultimately accomplishing the same kind of thing. Before we get to any of that, I'd like to do a little bit of a quiz on what we had done last class. So I'll leave this QR code up here for just about 5 seconds, and then I'll pop over to my Mentimeter for what we were doing. Okay, I'm going to pop over to the Mentimeter. The instructions for joining should still be on the Mentimeter there. Okay, I'm going to start the quiz. Okay, good. The main side effect from calling fork is that our PCB for the currently running process is duplicated. That is the main side effect. In terms of the way our OS is representing processes as these things that are running in the system, the main side effect is that our process control block has been duplicated. I want to dig into what this says. The process, so now we're talking about just one process here. We're just talking about one single process. The process begins to run 2 different branches in the program. I'm being extremely pedantic about this, to be clear. I'm being super pedantic about this, but this says that there's one process and it's doing 2 things at the same time. That's what that statement says, and that's why I've marked this as not the correct answer here. This statement says there's one process that's doing 2 things at the same time, but that's not actually what's happening here. We have 2 physically separate processes that are running the same code. They're running the same code. They've duplicated the code section of this address space that we have for the process that we started with, but now we've got 2 things that are running at the same time. And they have varied contents of their memory in the form of the return value from fork. That register has been changed in each of the process's control blocks that we've duplicated. So it causes them to have different branches in that same code section, but they're physically separate processes. So they're not the same process that's running. Does that make sense, everybody? So really specific difference between the processes doing 2 things and there are 2 processes doing the same thing. Okay, awesome. The next question has to do with some code that I want to show you in my terminal here. Here's the code. Is that big enough for everybody to see? The question I'm going to ask you about is, what's the output from this program? So I'm going to leave this up here for 10 seconds. I'm going to switch back to Mentimeter to start the question, and then I'm going to rapidly put the code back up because the code is not in the question itself, okay? Okay, I'm going to go back to Mentimeter. I'm going to hit enter, and I'm going to bring the code back up. Okay, good. I'm actually really happy that we picked these two options specifically and none of the other options. So let's step through this for a second. On line 4 here, we have one process running. There's just one process running, and so we print high. Just once, we print high once. On line 5 is where we're doing the whole duplication of processes thing. So we're separating into two processes at this point. The printf high on line 6 here is going to get printed twice. Once by the main parent process, and then again by the child process. Both of them are returning from our fork here. They've got different values in that child PID variable. And so they each do this printf, but then only the child process is going to run line 8 here. In only the child process is that value going to be 0, so the child's output here gets printed once. So I'm happy to see that nobody picked that middle option there where it prints out twice. And the last part here is, this is not good C programming in my mind, where I don't have curly braces around this, but just for like keeping it short, this last statement now is going to be outside of the conditional statement. So this is going to get executed by both of the processes that we have running. So we'll print by out twice. Related to Dogman, this character here is Lil Petey. And part of the plot of Dogman, you are all going to love Dogman by the end of this course. The plot in Dogman is that Petey, who is the evil cat, the villain in this book, decides that the best way that he's going to make progress as a villain is to clone himself. And so he orders a cloning machine, and he plucks one of his whiskers off and dumps it in the cloning machine and follows the step-by-step instructions to clone himself. And then out pops Lil Petey here as saying Papa, and Petey turns the paper over, and the last step is wait 18 years for your clone to grow to adulthood. And then it says immediately underneath of it, no refunds. And so cloning here, the clone idea is Lil Petey's a clone, and kind of acts like a child. Yes, welcome to my brain. Welcome to my brain. Okay. Here's the next, here's the leaderboard. Here is the leaderboard, okay? Cake, okay, congratulations, Cake, so far. We've got 2 more questions. So there's no code for this question. Here it is. All right, awesome, yes. So yeah, using wait. Wait is the key function that we really, really want to use if we're trying to wait for our child process to terminate in most cases, but it will also let us block for other things. Using get, char, and read, yes, technically they could satisfy that. We could just, have a get char in our parent process and have a printf that says, when the child process prints that it's exited, press enter. Yes, we could accomplish it that way, but the most reliable way here is to wait until the child process has exited. Okay, awesome. And here's the last question. Okay, so yes, replace the address space of the running process is the best answer here. This is 100% the best answer for this one. Here is a program. Here is a compiled program, and I would like you to take this compiled program and basically replace my entire address space with the contents of this one. The important part of replacing the address space here that causes our functionality to change ultimately is that the code segment is being replaced. That's the key one that's being replaced, because we're replacing the code segment and setting our program counter to be whatever the thing is after the main function. Start executing here. Give control of our process to another process. I'm being, again, really, really pedantic here. We're not giving our control of our process to another process. We're giving our control of our process technically to another program. We're handing off to another program, some inert thing, and we're saying, here, take all the code for this thing and stuff it into my code section, and I will never get control back again. Replacing input and out standard I/O with other files, block until the child process exits, and duplicating the PCB of the running process. Duplicate the PCB, that's the fork system call that we're doing here. Replacing standard I/O, this is something that we're going to be thinking about in terms of open file table, and then replacing the entries for standard input and output. And block until the child process exits is our wait function. Oh, I was not expecting that. Okay, congratulations, Ronald. Congratulations, Ronald. And then congratulations, everybody else, for keeping up here. Thank you. All right, let's pop back here. Let's talk about inter-process communication. One of the things that we have kind of been able to see with fork and wait is that our processes, they can sort of talk to each other, sort of. The main way that we can communicate between our processes through variables is to change the value of a variable immediately before we call fork. Have a counter that changes as you call fork, and then that child process has that value in it right now. Increment that value, call fork. Increment the value, call fork. Increment the value, call fork. And every child process is going to have a different value in that specific variable. But once we've done the fork, the only real way that we've seen for a child process to communicate back to a parent process is for the parent process to wait for that child process to exit. That's the only thing that we've been able to see. But in some cases, we need to be able to have our parent process giving data out to these child processes, or alternatively, we need to have more granular control of when things are happening between the child and parent process. Waiting until your child exits or dies is like not granular at all. It's finished now, but I want to know things like, how much progress have you made? What stage of this thing are you on right now? So we need to be able to communicate between processes after this fork system call has been made. We're going to look for today at the use of signals. Signals are a pretty primitive way to communicate between two different processes. And the limitation that we have with signals is that our processes are going to be able to communicate actually two things. One is that an event has happened, something happened. And two, it's who told me that event happened. That's all that we can communicate with signals. And that's good enough most of the time. That's good enough most of the time for the kinds of things that we're going to look at here. Something has happened are events that can be things like a bunch of my child processes or me and my child process are trying to access a shared resource. And I can signal to my child process that, hey, it's okay for you to start reading that file now because I've finished writing to it. You should wait until I finish writing and then you can proceed reading this file because I'm finished with it now. Shared resources and the like highly abstract physical world representation of this is literally this kind of a signal. We've got this intersection and we're trying to say, okay, it's the signal says walk now. Yeah, pedestrians can start walking across the street. And the signal is that people who are driving cars have a red light. You should not use this shared resource right now. Another way for this to think about this is I'm going to send a signal to a bunch of processes. I want you to wait around, and then I want you to all start doing the same thing at the same time. The same time. Hand wavy the same time because there's lots of other abstract things that are happening underneath this, but I want everyone to block until some event has happened, and then everybody's allowed to get started on this thing at approximately the same time. The other way is that we can kind of indicate not just shared resources, but like, hey, this thing is ready for you specifically now, and you can start working on this thing. So some event has happened that says, hey, look, I've got something to work with right now. I can now proceed to open this file and begin to do work with it. How many of you are currently in Comp 3350? Many, many, many of you. Okay, so in Android, because you're all doing Android projects still? Yeah, in Android, there's this idea of a message bus where you can kind of like register for events to happen, you know, button clicks and stuff like that. Signals is like the lowest common representation of this whole thing. If you have this idea of what the asynchronous events are doing with Android, button presses and like notifications appearing and stuff like that, you kind of already have an idea of what signals look like, except we're going to do it in C and not Java or Kotlin. Yeah.
Similar to like the JavaScript DOM events?
Is it similar to JavaScript DOM events? Yes, in a hand wavy sort of similar way. It's kind of like we're going to act on an event that's happening. The biggest differences between Java and Kotlin and JavaScript events is that when you receive those events, you're getting objects that have a lot of information about the event that's actually happening. And what we're going to see with signals here is we don't have hardly any of that stuff. All we're going to be able to see is that an event has happened, and then there's going to have to be external coordination between our processes to say stuff like, okay, if you want more information about this, we'll agree that you should read this file when you receive this signal from me. Yeah, yes. Yeah, just like everything in C, you kind of have to start from the bottom. The Signals API overall is honestly pretty straightforward. There's two different ways to do this, and we're going to look at the way that gives us the tiniest bit more information because it's the modern, I'm putting a giant air quotes here, it's the modern way to do it because at least it's you know, less than 25 years old, I think, as opposed to being 30 or 40 years old. The steps are, I should have a process that registers a signal handler. Registering a signal handler is going to be me as a process calling a function. And the two functions that I could call to do this are either signal as a function or sig action as a function. And we're going to call sig action in this class. What this is doing for us is we're asking the operating system, when somebody sends this signal to me, what I want you to do is run this function in my address space. I want you to run a specific function in my address space if somebody else sends a signal to me. And then I do stuff. I proceed with calculating pi, or I just go to sleep a bunch of times, or I start reading a file and processing it. I do other stuff that I want to do in my process. After a while, some other process is going to send me a signal. And that signal is going to be sent to me using either the kill program or the kill system call. Kill is a terrible name. Kill is the worst possible name for what this function actually does. It's used frequently to ask processes to terminate, to end now. I want you to stop, please. It's frequently used for asking them to stop, but it's very generally used to say, I want to send this signal to this process. The goals here that we're going to have with the code that we're going to write today are, I want to be able to send signals to other processes using kill, the command, and then also kill, the system call. I want us to be able to observe what's happening when a signal is received by our process that's running. And I want to figure out which signals that we are not permitted to handle, which we are not even allowed to handle, and kind of what happens when we are not allowed to handle them. So what happens when we can't handle them, and why we can't handle them. I'm going to be working from some code that I've posted up on the course webpage. I've posted a link to this repository. This one is called Interprocess comms. And I'm going to clone this. If you want to follow along with me, you should be doing this on a Linux system. This actually should work okay on Mac OS, but I didn't test it on Mac OS. So I'm not going to promise that it works on Mac OS, but it should work on Mac OS. If you want to follow along with me with what I'm doing on Aviary, please make sure that you are connecting two terminals to the same bird. So connect to Aviary once to figure out what bird you're connected to, and then connect directly to that bird in another terminal so that you have two connections to the same terminal. This is important because the kill command and the kill system call only work on the same machine. They're not going to work across different machines, so they have to be on the same machine. I'm going to be doing this locally on my machine. So I'm going to pop over here to my other terminal, and I'm going to change out of this directory to lecture 15, and then I'm going to pop open another terminal here, and I'm going to change into that directory to make sure that I have an actual directory, another terminal open in the same directory as that one. All right, so I'm going to git clone this repository to start. And what this repository contains within it is just a couple of things. The main thing that I want us to take a look at is this file that's called signal.c. I'm not going to read the README to you because I'm going to verbally tell you what the README says right now. This is a pretty short program to start. It doesn't do anything. It literally does nothing except for printing something out and then sleeping forever. This is something that will just run infinitely. We're doing some things that are a little unusual in terms of what we may have seen before. I have this structure here that's using this thing called a bit field. That's this colon here. And what this is doing is keeping this uint 8t, this unsigned integer, to exactly 2 bits. So it can only ever have 4 values, 0, 1, 2, or 3. And then if we add to that, it will just overflow back to 0 again. I'm using that to be an index into this indicators array that I've got on line 15 here, where it's just a dash and then a backslash and then a pipe and then a forward slash. And then we just increment count forever, print out that symbol and the carriage return, and then do it all over again after we go to sleep for a little bit. So I'm going to zoom out of this. I'm going to make this code, and if I run signal, it just does this forever. It's going to do this forever. I want to send my first signal to this process. The first signal that I want to send to this process is that I want you to stop, please. I would like you to please stop doing what you're doing and give me back control. The way that I'm going to do that is that I'm going to hit Control-C on my keyboard. Control-C is sending a signal to the process that says, please stop what you're doing and gracefully exit. Please close any files that you might have open, flush any buffers that you have open right now, and just gracefully exit. I'm going to open up a manual page here. This is Man7 signal. This is one of the ones that I pointed at for the readings for this week that are optional. What I want to point at here right now is the kinds of things that happen when we send signals to processes and the list of signals that we can receive from a process. There's a bunch of signals that can be sent and received. And I'm going to go down here. This is the list of standard signals that we can send and receive in processes. There's a long list of them, but the one that I want to tell us that we have just sent to this process is SIGINT. SIGINT is interrupt. Please politely stop what you're doing and exit. I mean, it doesn't really feel like that because when we're doing Control-C, we're doing it because we've entered an infinite loop and we definitely just want it to stop whatever it's doing. But Control-C is sending a signal that says, please politely stop what you're doing and exit. The default action here, this is this column this is the third column, 1, 2, 3, this is the third column. And the default action here is terminate. That basically just means the default action is exit. Call the exit system call and let the operating system clean up on our behalf. I'm able to send this signal using another program as well. And the way that I can send that signal is, I'm going to run this one more time, is to use the kill program. The kill program will take one argument, and I'm going to send it sigkill. And I want to send it to a specific process ID, so 406981 here. This is now two completely unrelated processes sending messages to each other. Remember that our shell, when I hit enter on my keyboard here, is doing fork, and then it's doing exec on this kill program. So I've caused a new process to start. Kill is starting. It gets as its second argument sigkill. I'd like you to send the sigkill or sigint signal to this process. Interrupt and 407215. I would like you to stop politely what you're doing and exit. My shell forks and execs this. This is going to send a signal to this running process right now. We haven't done anything other than causing these things to be sent to our other program. Terminating is not a useful way to send and receive messages. That's not exactly what we want to accomplish with this. And so what we're going to do is we're going to change the behavior of what's happening when we send and receive signals between these things. So I'm going to go up to the top of my code here, and I'm going to start adding some new includes. And what I'm going to tell you, I'm not going to read this right now to you, but if you go to man2 signal, and then also to the other one I'm going to look at is man2 sig action. These are where you can get information about how to write these things, how you can use these things, but I'm just going to verbally tell you what to do with this right now. So I'm going to include signal.h at the top of my program. And what I need to pass to our signal handler function is ultimately it's going to be a function pointer. So the way that I'm going to define what my code should do in the event of receiving a signal is I need to declare and then define a function, what it should actually do when this happens. The function signature for this should be it doesn't return anything, It can be named whatever you want, but I'm going to call it handle signal. And then it takes 3 arguments. The signal number that was passed to us. So sig int is a numbered signal, sig term is a numbered signal, sig bus is a numbered signal, and then all of the things that we saw in the list are all numbered signals. The second argument that this accepts is a structure of type sig info underscore t pointer. And I'm going to call this variable info. And then the last thing that it receives is this thing called a context. We are going to completely ignore. We're going to set up a signal handler. We're going to completely uContext. Verbally, I will say to you that this is approximately parts of our process control block. It will have things in it like registers and stuff. And then beyond that, we're not going to think about it. We are just going to completely ignore that this third argument is even passed to us. I welcome you to explore this structure on your own time in your own debugger, but we're just going to ignore that this is a thing that happens. In my signal handler, I'm going to start with minimally printf, handling signal, %d, new line character, signum. I've got a signal handler now. And what it's going to do is print out the number of the signal that was sent to it. This is not enough, though. I need to actually register this signal handler in the operating system side. And so the way that I'm going to do that is I'm going to call in my main function a new function that's called sigaction. Sigaction takes a couple of different arguments. It's going to take the signal that we want to handle. So the one signal that we've seen right now is sigint. I'd like to be able to handle the interrupt signal. The second argument that it takes is a handler, and we're going to get to that in a second. And the third argument that it takes, I'm going to tell you, is for us, for now, null. It doesn't take a third argument, but we have to specify what that value is. The second thing that it takes is what it should do when it receives this signal. And to do that, we have to declare an instance of this struct that's called sigaction. So I'm going to say struct sigaction, and I'm going to call this handler. And I'm going to use a new kind of initialization of a struct that you may not have seen before. So previously, we've been initializing these things with that 0 in the curly braces. Another way that we can declare and initialize instances of structures is to use this dot notation. In the manual page, you'll find a description of what this structure looks like. Again, I'm just going to tell you what it is for now, just to get us moving with this. The first thing that it takes that we want to set in here is this thing that's called SA sigaction. And I want to initialize this to the function that I want to actually handle the signal. So handle signal is saying here, I want this function called when the signal is received. So when my process receives this signal, that's the function that should get called by this thing, and it has to have the signature that I've described above. So void, a name, it accepts as input an integer, a siginfo pointer, and then a void pointer. And the last thing that I want to do here is I'm going to add one more argument, or one more value for this, that's SA flags. And SA flags is going to be, I'm going to give it this value SA sig info. What this means ultimately is that there's an old way to register signal handlers and a new way to register signal handlers, and we're telling it we want to do it the new way. I'm going to have 3 arguments instead of just one. SA sig info says you should populate the second argument to this function that I'm going to ask you to call on my behalf. So once I've done that, I'm going to pass a pointer to my handler. This is an instance of the struct that I've declared on line 27. And I'm going to write this. I'm going to zoom out. I'm going to make it I'm going to go back up to the top here, and I'm going to put a void in front of this. I'm not using this variable, and I will not use this variable. And I'm going to put a void in front of that one. I will use this, but I'm not going to use it right now. OK, so we're able to compile our code. I'm going to run it. The output has not changed. That actually kind of makes sense. All that we've done so far is on line 36 of this code, we've said, hey, operating system, when you are going to send me the signal that is sigint, I would like you to run this function, please. Our operating system in the process control block is going to say, well, the default value was exit. The default value was exit. That was the signal handler by default for sigint. Now I'm going to call this function instead. So we can imagine this as a signal handler table. There's indexes into this table and function pointers, and these are the things that should get called when this function this signal is received by this process. And we've replaced the default action with this new action. And so now I'm going to send this process a sigint. I'm going to hit Control-C on my keyboard. And then I'm going to panic because, oh no, how am I supposed to stop this process from running? Control-C was the way that I caused these processes to stop running. Oh no, I'm going to kill sig kill. And then I actually forget what the process ID was for this. So I'm going to run PSA. And then I'm going to run kill sig kill on 407765. And that will cause it to end. That causes it to end. OK, so in my process, on line 36, I say, please do this instead. Operating system, in your process control block, when you are about to send me a sigint, I would like you to run this function. The default action was exit, but now I want you to do this instead. My process then continues here to just sit here and spin around forever, printing out these nice shiny animation of a spinning little indicator to say, yeah, I'm doing something. I'm making progress and I'm doing something. Eventually, Franklin comes along and hits Control-C on his keyboard to send this signal to my process. And what our operating system does is it receives the signal. We're not sending the signal directly to this process. We are sending the signal to the operating system. And we're saying, hey, operating system, please send this signal to this process number. When I hit Control-C on my keyboard, that's my shell keeping track of, this is the currently running process, and this is the signal that I should be sending to this other process. My operating system is going to say, all right, thank you for letting me receive that message. I will forward it on your behalf. The operating system then goes to the process control block for the process ID that was specified by that kill or by that Control-C. It looks in this table that has all of these signal handlers, and hand wavy, really, really hand wavy, what it does here is it inserts a stack frame into whatever it was doing before. It doesn't matter what it was doing before. We were down here in this loop doing right, right, sleep, right, right, sleep, right, right, sleep. And our operating system is going to interrupt. I don't care what you were doing before. You are now executing this function. I pushed this onto your stack. You are going to start running. Your program counter is going to be set to be this function. And I'm going to do this printf. And then I'm going to return from that function. That stack frame will get popped off. And I will just go back to whatever it was I was doing before. Right, right, sleep. Right, right, sleep. Receive signal. Stack frame gets pushed on. I print this message out. And then I return and go back to whatever I was doing before. Right, right, sleep. Right, right, sleep. one of the things that we just did was we sent sigint to a process 408058, and it caused it to print that message out. When I hit Control-C here, it does the same thing. I'm accomplishing the same task. I'm asking this process to do sigint, to do the action that it has for sigint. But what I've also done here is I've said 408 sigkill to 408058, and now it gets killed. So my thought here is, all right, I'm going to copy this line and paste it, and I'm going to say for sigkill, I would also like you to just print out this message. I just want you to print out that message. I'm going to make this code again. I'm going to run it. I'm going to hit Control-C. The same thing's happening. I'm going to send sigint to 408213. The same thing is happening. I'm going to send sigkill. I am not allowed to handle that signal differently. I'm not allowed to handle that signal differently. I'm going to leave this for you to think about for a second. I'm going to actually leave this for you to think about until all the way of next class. Why? Why am I not allowed to register a signal handler for sigkill? Why would I be not permitted by the operating system to register a signal handler for sigkill? So just think about that. There's one last thing I want to do here that's going to result in another question. So why does this line below have no apparent effect in the OS? The other thing I want to do that I'm going to leave with a question here is I'm going to add some code to this. I'm actually going to use this siginfo structure. And what I'm going to say is I'm going to say printf received from %d info arrow and then si underscore pid. So this siginfo t structure gives me some information about who sent the message to me. I'm going to make this one more time. I'm going to run it one more time. I'm going to hit Control-C on my keyboard once, twice, 3 times. And then I'm going to say kill sigint 408356. Why is that process ID changing every time? Just think about this. No responses right now, just food for thought for right now. My hint to you about this is, what is my shell doing when I hit enter here? And what is my shell doing when I hit enter here? And what is my shell doing when I hit enter here? And what is my shell doing when I hit enter here? Okay, we will come back to finish this up on Wednesday. But at this point, you should be able to write code where processes communicate through signals. You should be able to register a signal handler, and you should be able to send signals using the kill command. You should be able to, at a high level, describe how our operating system is supporting this use of signals, supporting the implementation of signals. And you can't really compare any of this yet, but we'll think more about this as the course is going on, especially as we get to threads. Thank you all for coming out. I hope you have a good rest of your day, and I'll see you all on Wednesday. Bye.